I want you to think about the last time you stubbed your toe.
Oh, the worst.
Right. Like you are walking through your dark bedroom, maybe half asleep, and suddenly smack.
Right into the bed frame.
Exactly, the unforgiving edge of the bed frame. Now, I really want you to focus on the exact sensation of that specific moment. There is that initial, shocking, lightning-fast spike of sharp pain.
Hmm.
But right after that, there is this eerie split-second pause. You actually have enough time to think, oh no, this is going to be really bad.
You're just bracing for it.
Right. And then right after that thought, a massive, throbbing, dull ache just washes over your entire foot. It is a completely bizarre two-part experience.
It really is, yeah.
And to find out why your body actually does this, we are jumping into a massive stack of sources for today's deep dive. We've got clinical physiology texts, historical research papers, and even some modern genetic case studies.
It's a really comprehensive stack.
It is, and our mission today is to map exactly how the human body signals pain and, why the difference between a sudden injury and chronic pain is so misunderstood.
Right.
Because modern science has basically shattered this old idea that pain is just a simple biological alarm bell ringing in your brain.
Oh, completely. I mean, it is a total paradigm shift. By the time we are done going through these sources, you're going to understand why rubbing a banged elbow actually makes biological sense.
Which I always just thought was a placebo thing, honestly.
Right, but we'll see why it's not.
Ah.
And we'll also look at why placebos themselves are, well, completely real physical responses.
Oh.
And ultimately why pain is something your body actively constructs rather than just something it, passively reports.
Which is wild. But to really appreciate how complex the system is, I think we first need to talk about how wrong humanity was about pain for centuries.
Oh, yeah. We were so wrong.
The sources point us back to René Descartes in the 1600s, and he had this very intuitive idea about pain.
Yeah, in his 1664 Treatise of Man, Descartes used this really straightforward analogy. He basically said, imagine a fire touches your foot.
Okay.
That heat pulls a little fiber in your leg, which runs in an unbroken straight line all the way up to your brain.
Like a literal string.
Exactly like a string.
Mm-hmm.
And when it gets to the brain, it rings a bell. It is just like pulling a rope to ring a bell in a church tower.
Which honestly makes sense.
It does. This became known as specificity theory. The whole idea was that pain is a hardwired straight line alarm. The more tissue damage you have, the harder the rope is pulled, and the louder the bell rings in the brain.
Right, it's just pure logic. If you cut your finger a little bit, it hurts a little. If you cut it a lot, it hurts a lot.
Exactly.
But the sources show that this theory eventually collapsed, right? Doctors started noticing things that just did not fit the whole rope and bell model at all.
Right. By the mid-20th century, the medical community just could no longer ignore the anomalies. And the most glaring one was phantom limb pain.
Oh, wow, yeah.
You have these patients who have had an arm or a leg amputated, right?
Oh.
Yet they're experiencing excruciating, burning pain in a limb that literally no longer exists.
Because if pain is just a rope attached to your foot,
How in the world is the bell ringing when the foot and the rope have been completely removed?
it totally breaks the model. And that brings up another observation from the research that I actually had to read twice. It was from a doctor named Henry Beecher during World War II.
Ah, yes. The Anzio beachhead.
Right. He was an anesthesiologist treating soldiers there in 1946. And these soldiers had just catastrophic, horrific combat wounds. But he noticed that compared to civilian patients he treated back home for similar, surgical injuries, these severely wounded soldiers rarely even asked for morphine.
It's such a striking detail.
It is. Only about a quarter of them even wanted it. So the obvious question is, why would a soldier with a massive injury feel less pain than a civilian with a routine surgery?
Because the context fundamentally changed the experience.
How?
Well, think about it. For a civilian back in a hospital, a major injury meant lost wages, disruption to their family, and just profound fear.
Right. High stress.
But for a soldier pinned down on that horrific beachhead, the injury had a totally different meaning. It meant survival.
Oh, wow.
It meant they were alive, the fighting was over for them, and they were finally going home. So Beecher concluded that the meaning of the injury actually altered the conscious experience of pain.
The physical tissue damage was the same in both groups.
Exactly. But the perceived pain was radically different.
So the brain isn't just a bell waiting to be rung. It's actually interpreting the situation in real time.
Precisely.
Okay, let's unpack this. Because that realization forced the medical community to rewrite the rule book entirely. If you look at the International Association for the Study of Pain, they finally updated their official definition of pain recently, and it is a massive departure from the old Descartes model.
It really is.
The 2020 update explicitly states that verbal description isn't required, so obviously infants and animals feel it too. But the biggest change is that they say pain is always influenced by biological, psychological, and social factors every single time.
What's fascinating here is that this update officially dethrones the old rope and bell theory once and for all. It confirms that pain is not a passive readout of physical damage.
It's an active process.
Exactly. It is an experience that your nervous system actively constructs. Your brain takes in all these competing data points, the actual physical damage to your tissue, your current stress levels, your past trauma, your environment, and it builds the sensation of pain in real time.
Okay, so if pain isn't just a single string pulling a bell, what is the actual biological hardware doing? Like if we go back to that stub toe in the dark bedroom, what is the literal physical sequence of events happening in the body?
Okay, physiologists break this down into 4 distinct stages: transduction, transmission, modulation, and perception.
Okay, 4 stages.
Yeah. Let's start at the very edge of your body, in the skin of your toe. You have these specialized free nerve endings called nociceptors. But it is crucial to understand that nociceptors do not actually feel pain,
Wait, if they are the pain receptors, how do they not feel pain?
because nociception and pain are 2 different things entirely. Nociceptors are basically just environmental hazard detectors,
Like a smoke alarm.
exactly like a smoke alarm. They're tuned to extreme stimuli. They look for extreme heat, specifically anything above 43 degrees Celsius. Or they look for intense mechanical pressure, like your toe hitting a bed frame.
Right, okay.
Or they look for chemical irritants released by damaged cells, like histamine. When you stub your toe, that mechanical crush causes the nociceptor to fire. It takes that physical pressure and translates it into an electrical signal.
And that's stage 1.
Right. That translation is step 1, transduction.
So nociception is just the encoding of the data. It's a warning signal, but it isn't like pain yet because the brain hasn't processed it. Sort of like when someone is under general anesthesia, their nociceptors are still firing if the surgeon makes an incision, but the patient doesn't feel pain.
Precisely. The warning signal is sent, but the brain isn't awake to construct the pain experience. So once that physical impact is translated into an electrical signal, we move to step 2, transmission.
Right.
Those electrical signals need to travel from your toe, up your leg, and into your spinal cord. And they do this by traveling along 2 very distinct types of nerve fibers. Think of it as a 2-lane highway.
Oh, is this why we get that weird 2-part sensation when we stub our toe? The initial sharp pain, the pause, and then the dull ache?
That is exactly why. The first lane of this highway is made up of what we call A-delta fibers.
Which the sources described as the sports cars of the nervous system.
Yeah, that's a great way to put it.
They have this thin layer of insulation around them called myelin, which apparently allows the electrical signal to travel incredibly fast, like up to 30 meters per second.
Yes. So the millisecond you hit the bed frame, that A-delta sports car zooms up to your spinal cord and delivers that initial, sharp, piercing pain.
The first pain.
Exactly. It is highly localized, meaning you know exactly which toe you just hit. And it demands your immediate attention, so you stop walking into the bed frame.
Right, it's telling you to back up.
Yeah.
Then comes the second lane, the C fibers.
Dump trucks.
Right. If the A-delta fibers are sports cars, the C fibers act like slow-moving dump trucks. They don't have any of that myelin insulation, so the electrical signal just crawls along at under 2 meters per second.
And that dump truck is carrying the heavy, agonizing, dull, throbbing pain. The second pain.
Which explains the pause.
Exactly. Because it moves so slowly, it literally takes a full second or 2 longer to arrive at the spinal cord than the fast sports car signal. That is the terrifying pause you experience. The physical speed limit of your uninsulated nerve fibers is what creates that delay. You can literally time it.
That makes perfect sense. So the sports cars and the dump trucks race up your leg, and they both arrive at the spinal cord. Does the signal just shoot straight up into the brain from there?
No, and this is where the system gets truly brilliant. This brings us to step 3, modulation.
Okay.
When these nerve fibers enter the spinal cord, they don't just have a free pass to the brain. They pull into a highly regulated relay station in an area called the dorsal horn.
The dorsal horn.
Right. And in 1965, two researchers named Ronald Melzack and Patrick Wall published this revolutionary paper proposing what they called the gate control theory. They argued that this relay station acts like a literal gate.
Like a bouncer at a nightclub deciding who gets to go in and who stays out.
Exactly like a bouncer. The gate can open wide to let all the pain signals through to the brain, or it can actively close to block them.
Okay, this has to be why we instinctively rub an injury.
Yes.
Because if I bang my elbow on a doorway, the very first thing I do without even thinking is grab my arm and aggressively rub it or shake it. And we all do it because it genuinely makes it feel better.
Yes, and Melzack and Wall's theory explains the biology of why that works. When you aggressively rub your banged elbow, you are activating a totally different set of nerves called a beta touch fibers.
Okay.
These are large, fast, pressure-sensing fibers. They are not detecting pain, they are just detecting normal touch and pressure.
Right.
But when these fast touch fibers fire rapidly, they send signals to that same bouncer in the spinal cord. And the bouncer responds by physically inhibiting the transmission of the slower pain signals. It literally closes the gate.
Wait, so rubbing it isn't just a mental distraction. You are mechanically blocking the pain pathway.
It is pure mechanical inhibition. This is the exact mechanism behind 10NS units, those little electrical pads physical therapists stick in your muscle.
Oh, yeah, they buzz.
They flood the nervous system with a non-painful electrical buzzing sensation. Those buzzing signals rush the gate, keep the bouncer busy, and prevent the actual pain signals from getting through to the brain.
That is so cool. Okay, so I've rubbed my elbow, I've closed the gate as much as I can, but, some of that pain signal still gets past the bouncer. What happens when it finally hits the brain?
That is step 4.
Yeah.
Perception. The signals that survive the spinal cord travel up into the brain, hitting a structure called the thalamus.
It's thalamus.
Yeah, and the thalamus acts like a massive switchboard. It routes the pain data to different areas of the brain simultaneously. It sends a signal to your somatosensory cortex so you can physically map the pain on your body.
Right, so you know where it hurts.
Exactly.
Yeah.
It sends a signal to your limbic system, specifically the anterior cingulate cortex and insula, to generate the emotional distress and panic. And it sends a signal to your prefrontal cortex, which tries to assign logic and meaning to the pain.
Like beacher soldiers realizing they were safe.
Precisely.
But the brain isn't just a passive receiver, right?
Yeah.
The sources talked about something called descending modulation. Does the brain actually send signals back down to the spinal cord to fight the pain?
It does. When the brain registers severe pain, the brainstem, specifically an area called the PAGI, can send signals back down the spinal cord to that original gate, commanding it to shut completely.
Whoa.
And it does this by releasing its own natural painkillers. Your body has a built-in pharmacy. It produces endogenous opioids, chemicals like endorphins and enkephalins. In high-stress situations, your brain can flood your spinal cord with these natural opioids and effectively mute the pain from the top down.
Which perfectly explains the study from 1978 that absolutely fascinated me.
The Levine study.
Yes. So a researcher named John Levine looked at patients recovering from dental surgery. They were in pain, obviously, and his team gave some of them a placebo, just a simple saline injection, but told them it was a powerful painkiller.
Right.
And a lot of those patients reported profound, genuine pain relief. Wait, so the brain is literally acting as its own pharmacy just based on expectation.
It is. Historically, doctors would have dismissed that.
Yep.
They would have just said the pain relief was all in the patient's heads. But Levine went a step further to prove what was biologically happening.
What did he do?
After the patients felt better from the placebo, he gave them a drug called naloxone. Now, naloxone is an opioid antagonist. It physically binds to opioid receptors in the brain and blocks them. It is the exact same drug paramedics use today to reverse heroin overdoses.
Okay, so if the placebo effect was just psychological, just in their heads, then naloxone shouldn't do anything.
Right. It shouldn't have any effect.
Right.
But when Levine gave the patients naloxone, their pain immediately came rushing back.
Oh, wow.
The placebo effect completely vanished.
That is incredible. So the naloxone blocked the relief, which means the placebo wasn't just fake positive thinking.
If we connect this to the bigger picture, it means the belief that they were getting medicine caused their prefrontal cortex to signal the brainstem to actually manufacture and release real physical endogenous opioids.
Expectation altered their biology.
Exactly. The body synthesized its own painkiller based purely on belief. This single finding revolutionized medicine because it proved that placebos trigger a measurable physical mechanism in the pain pathway.
It's not magic, it's just biology.
Right. It is why every clinical drug trial today has to be double-blind and controlled for placebos. You have to prove your new drug works better than the brain's own ability to manufacture painkillers.
Okay, so we have spent all this time talking about how brilliant the system is at protecting us. The nociceptors fire, the gate modulates it, the brain interprets it, and even sends down natural painkillers. But what happens when this perfectly tuned system breaks?
Well, it can break in two main ways. It can either fail to fire at all, or it can get stuck in the on position.
Let's start with when it doesn't fire.
Okay, if we look at what happens when it fails to fire, the sources detail a remarkable genetic case study from the mid-2000s. Researchers Woods and Cox looked at several families in northern Pakistan who carried a rare genetic mutation in a gene called SCN9A.
SCN9A, right.
This gene is responsible for creating a specific sodium channel, NaV1.7, which is absolutely essential for that very first transduction step in the nociceptors.
So without that sodium channel, the nociceptors just can't translate the physical pressure into an electrical signal.
Correct. The physical damage happens, but the electrical warning signal is never generated. The individuals with this mutation have a condition called congenital insensitivity to pain.
On the surface, that sounds like a superpower. Like, imagine never feeling pain. But reading the case reports, the reality is incredibly tragic.
It is devastating. The reports describe young children accidentally biting through their own tongues while eating.
Oh my gosh.
They walk on broken legs without a limp because they have no idea the bone is fractured. They lean on burning hot stoves and suffer severe third-degree burns because they lack the basic reflex to pull their hand away.
It is a harsh reminder that acute pain is a highly evolved, vital survival mechanism. We need that initial alarm to keep us from destroying our own bodies.
Absolutely.
Here's where it gets really interesting, though. If acute pain is the alarm that saves your life, how does chronic pain fit into this? Is chronic pain just an acute alarm that gets stuck in the on position?
That is exactly how the medical community used to think about it, and it was a catastrophic mistake.
Really?
Yes. Chronic pain is not just acute pain that lasted too long. It is a completely different disease process. To understand it, think about a severe sunburn. When you have a really bad sunburn on your shoulders and you step into a lukewarm shower, what happens?
The lukewarm water, which normally feels great, suddenly feels like you're being scalded with boiling water.
Exactly. That phenomenon is called allodynia, when a normal, harmless touch suddenly becomes agonizing.
Right.
There is also hyperalgesia, where something that should only hurt a tiny bit ends up hurting immensely.
Right.
These are the hallmarks of a process called sensitization. When your nervous system is exposed to ongoing injury or severe inflammation over a long period, it starts to physically change.
Wait, the nerve fibers actually physically change structure?
Yes. The nociceptors in your skin become hyperexcitable. That is peripheral sensitization. But the real nightmare is central sensitization.
What happens?
The repeated barrage of pain signals actually alters the physical structure of that relay station in your spinal cord. The synapses get stronger, the bouncer at the gate essentially gets fired, and the door is left wide open.
Oh, wow.
Even the maps in your brain start to blur and reorganize. The volume dial on your entire nervous system gets cranked to maximum, and then the dial snaps off.
So even if the original injury, say like a herniated disc in your back, completely heals, the pain pathway remains stuck in this hyper-amplified state. The hardware had been rewired.
Exactly. The tissue healed years ago, but the nervous system is permanently altered. We see this in neuropathic pain, too, like in patients with shingles or diabetic neuropathy. The high blood sugar in diabetes literally damages the nerve fibers. The pathway isn't just transmitting a bad signal, the pathway itself is broken and misfiring.
This distinction feels so critical, especially when we look at how medicine has historically treated pain, treating a rewired, broken nervous system as if it were just dealing with a temporary acute injury led to one of the most devastating public health crises in modern history.
The opioid epidemic.
Exactly. The sources specifically point to the 1990s and pharmaceutical marketing, most notably by Purdue Pharma with OxyContin in 1996.
Yes.
They aggressively pushed the idea that opioid pain relievers were safe and carried a very low risk of addiction for chronic pain patients. How did the medical establishment get it so wrong biologically?
Well, this raises an important question about how we treat pain globally.
Yeah.
They got it wrong because they applied an acute pain framework to chronic pain physiology. Exogenous opioids prescription pills, like oxycodone, work incredibly well for short-term acute pain, like after surgery.
Right, because they mimic those natural endogenous opioids we talked about earlier.
Exactly. They bind to the receptors in the brain and spinal cord, hijack that descending modulation system, and slam the pain gate shut.
But chronic pain is different because of central sensitization. The volume dial is already broken.
Right, because chronic pain has fundamentally rewired the nervous system, throwing massive amounts of prescription opioids at it causes a biological panic.
A panic.
Yeah. The brain senses this flood of opioids and says, whoa, this is too much, and it starts shutting down its own natural receptors to survive. It downregulates.
So it builds a tolerance.
Very quickly. The drug stops working for the pain, but now their brain has shut down its natural defenses. So when the pill wears off, the pain is worse than ever, and the physical dependence is locked in.
The hardware was fundamentally different, and by treating it with an acute pain tool, we didn't fix the pain, we just created addiction.
It's a profound tragedy.
It really underscores why understanding the actual mechanisms of the body is so vital. And before we wrap up, there is one last major misconception the sources tackle.
The dualism debate.
Yeah. It goes all the way back to Descartes and the idea of dualism, this lingering belief that pain is either real, meaning there is physical tissue damage, or it is in your head, meaning it is psychological.
Right, and the modern understanding of the pain pathway destroys that distinction entirely.
How so?
A researcher named Ronald Melzack introduced the neuromatrix theory of pain in the 1990s. It argues that all pain, every single instance of it, is generated by the brain's vast network.
So it's all in your head, technically.
Technically, yes. So-called psychosomatic pain is physiologically real. It is built from real neurons firing, real neurotransmitters, and real neural circuits. Just because the trigger might be severe stress or emotional trauma doesn't mean the pain is fake. The brain is constructing it the exact same way it constructs the pain of a broken leg.
The brain's interpretation is everything, but sometimes the brain's interpretation is just dead wrong, right? Like with referred pain.
Oh, referred pain is a fascinating quirk of our wiring. Think about a classic symptom of a heart attack.
Right. A person doesn't always feel a stabbing pain in their chest. They often feel it shooting down their left arm or up into their jaw.
Exactly.
Why does an organ failing in your chest make your arm hurt?
Because the sensory nerves from your internal organs, like your heart, and the sensory nerves from your skin, like your arm, converge on the exact same segment of your spinal cord.
Oh, I see.
They hand their signals to the same bouncer at the gate. When the brain receives that panic signal, it has to guess where it came from. Because it is incredibly rare for your heart to cry out in pain, but very common for your arm to get injured, the brain misinterprets the source.
So it projects the pain onto the arm.
It is a biological mapping error.
That is wild. Okay, if you step back and look at this mountain of information, so what does this all mean? I think there are 5 core takeaways you should walk away with today.
Let's hear them.
First, pain isn't just a bell ringing. It is a complex 4-stage process of transduction, transmission, modulation, and perception. The signal is constantly being amplified or dampened along the way.
Second, gate control theory proves that rubbing an injury actually works biologically. Those fast touch fibers physically close the gate in the spinal cord on the slower pain signals.
Third, acute pain is a life-saving alarm system that keeps you whole, while chronic pain is a distinct disease where a sensitized nervous system has fundamentally rewired itself.
Fourth, the latest medical definitions confirm that pain is always a subjective, brain-generated experience influenced by biology, psychology, and your social environment.
And finally, the opioid epidemic serves as a tragic cautionary tale of what happens when we mistake the broken hardware of chronic pain for a temporary acute alarm. We treated a deeply altered nervous system with the wrong tools.
It really shifts your perspective entirely, doesn't it?
It really does.
And I want to leave you with a final thought to mull over, something that builds on that neuromatrix theory. We know the brain can generate agonizing pain entirely without peripheral input, like we see in phantom limb pain.
Right.
The brain constructs the feeling of pain from a massive matrix of biological and psychological signals. And as we saw with Levine's placebo study, the brain can literally cure its own pain based on expectation alone.
Because it manufactures its own pharmacy.
Exactly. So if the brain is the ultimate architect of our pain, it raises a fascinating possibility. Could the future of pain relief bypass chemical pills altogether?
Oh, wow.
As we develop highly advanced virtual reality environments and non-invasive neural interfaces, could we one day learn to literally hack the brain's neuromatrix with software?
That's a crazy thought.
Instead of taking a pill with systemic side effects, could we teach the brain to simply locate the pain dial and turn it off from the inside out.
That is an incredible thought. It makes you wonder, the next time you stub your toe on that bed frame, maybe the ultimate cure won't be a pill or an ice pack. Maybe it'll just be a quick software update to your brain.
Exactly.
But until then, just keep rubbing it.
And let that bouncer close the gate.